So yeah, thank you very much for inviting me here. My name is Aravind. I'm working at OpenAI as a researcher. Today I'll be talking about Decision Transformer, a new architecture for reinforcement learning that we published at NeurIPS last year. So this was work done with Lily Chen, Kevin Liu, Arvind Rajeshwaran, Kimin Lee, Ditya Grover, Michael Laskin, Peter Abil, myself, and Igor Mordash, many people. Lily and Kevin were the undergrads who ran like many of the experiments in the paper, and Igor and I advised the project and when we were all in Peter Abil's lab. So this is actually a hybrid summit between deep learning and reinforcement learning. So this paper is actually like a pretty good fit for that because it's actually how a deep learning person would approach the reinforcement learning problem. If you're not familiar with the sequence like terminology or framework, this was the paper published in 2014 by Ilya Sutskever in Google Brain, where you basically train for any sequence-to-sequence task where you're provided an input sequence of tokens and you're outputting another sequence. You can just train a single recurrent neural network. Back then, people were using LSTMs that just take in all the input sequence token by token and tries to predict the output sequence token by token. So this was like deployed by Google for speech recognition, machine translation, image captioning, and so on, which we all use in our everyday lives. And this particular blog post by Andrei Karpathy shows the flexibility of this framework, where you can do like one-to-one tasks like image classification, one-to-many like image captioning, many-to-one like video classification, many-to-many like, for example, you do video captioning or machine translation for that matter. So there are like so many different ways in which it can be applied. So it's a very, very flexible framework to think about any problem that you may face in deep learning, or for that matter, even reinforcement learning, because you can consider reinforcement learning as the problem where you look at all the past sequence of states and actions, and you're basically trying to predict the future actions. So that is basically a sequence-to-sequence problem too, and that's the fundamental idea behind this architecture. In 2017, Google Brain published this like seminal paper, which basically is the rage of deep learning now, called the Transformer, which does away with all the recurrence in the old sequence-to-sequence architecture and just replaces it with pure attention. And I'm pretty sure that all of you are familiar with this now because this is like the bread and butter of like all the large language models and Google's BERT models, search, everything is running with transformers these days. And for those of you who are not familiar, I'm just borrowing this illustration from the original Google blog post where every single token is attending to every other token layer by layer. So the representation for any token in the next layer is a weighted combination of the representations of all the tokens in the previous layer. And these representations, which have high bandwidth access to all the positions in the sequence, are used to complete the output sequence token by token. Doing this allows you to train models which are much shallower compared to the old LSTM models because you're looking at all the positions all at once, and it is parallel in nature because it doesn't need to propagate one step at a time while doing the forward prop, and it's also like computationally very efficient that it can train the same train for the same performance in much less time. So this has basically replaced all the LSTMs and ConNets in pretty much most major deep learning applications now. So why did this really pick off? It's because of this particular architecture called GPT, which is a version of the transformer that just predicts the next word from the previous word, and it learns to do this at the internet scale of text, and natural language understanding emerges for free. So this is the OpenAI GPT architecture, and the way it works is you basically take a sentence, and then you're basically trying to predict the next word given all the previous words. And this can be done in parallel because the transformer is a parallel architecture, so you can do multiple predictions for any sequence at the same time, batch multiple sequences together, and look at like terabytes of data on the internet, and learn really general purpose representations. And the fundamental building block of this is the mass self-attention operator, which you're all familiar with from the transformer. So this is all just to give you a background of why the transformer is important. So the current modern version of GPT is GPT-3. Just for fun, while preparing the slides, I used the API and tried to generate like, what is a decision transformer? What would like GPT-3 think a decision transformer is? And it's reasonably accurate. So it might actually help people generate new paper ideas or write new papers in future. So just for fun, I'm going to read it through. Decision transformer processes a sequence of states and actions in the past that the agent has seen in order to, this was the prompt I gave it, and its completions are make predictions about the best state action pair to take in the future, which is pretty much what it has to do given the current state. The predictions are made by learning a function that takes as input a sequence of states and outputs a sequence of probabilities over state action pairs. I mean, obviously this is not the same thing we do in practice because state action pairs is high dimensional cardinality. So we just do it over actions. But still, like, you know, you can see that the models implicitly understood that, oh, transformer is a sequence model, RL is like predicting plans, and you kind of have to combine them together. And then you can also see how it's able to understand the advantage of decision transformers. It can scale to larger problems compared to traditional architectures, learn much richer representation of the environment, and you know, it's understanding like, okay, all the other stuff is like not real, like AlphaZero doesn't use DTs and all that. So, but still it's pretty cool. And this is fundamentally the crux of the architecture too. The reason I'm giving you all the motivation for transformers is also to touch on the whole universality aspect of transformers. So the same transformer which was used for NLP can just be used for images too by treating a pixel as a token. And that was able to do this thing called image GPT, where it's able to like do in-painting and so on. And it's basically also now replaced ConNets for like large-scale applications in computer vision too, where you basically just take an image, you break it into patches, and you treat each patch like a word in a sentence, and just throw the same transformer that's used in GPTs and BERTs, and you can train large image recognition models, which are currently state-of-the-art in most like computer vision benchmarks now. So, and these are like also have been shown to be more scalable in the Google paper called Vision Transformer. So this was actually summarized by Andre Karpathy in a really nice tweet thread, which I recommend you to check out. Basically, he says that you know, when he was when he was doing PhD, everything like NLP, speech, computer vision was all like reinforcement learning were all like so different from each other. So people were not really interested in what's going on in the other field because the architectures, the loss functions they were using were so different. And it's actually like only now that everything's sort of consolidating together, and because of transformers mainly. And he says that, but approximately the last 2 years, the neural net architectures across all these areas are starting to look identical, which is basically a transformer, and it can be written in 200 lines of code in PyTorch, which he actually did in a repo called MinGPT. And there are only very minor differences. Actually, for the decision transformer implementation was just built on top of Hugging Face, transformers, and MinGPT for our research. So it's literally like whatever he says is really true and how we did the research. And you can, and notice the final paragraph where he says you can feed in a sequence of words, you can feed in a sequence of image patches, or speech chunks, or a sequence of state action rewards for reinforcement learning. You can arbitrarily throw any amount of tokens in what you condition on in order to predict what you predict in the future. And it becomes like a super general flexible framework. And so that's why like this consolidation in architecture space will turn and focus like concentrate software and hardware and infrastructure. So if somebody figures out a new version of CUDA or like new kernels for speeding up transformers in computer vision, that's very likely to be useful for decision transformer. Or like if somebody works on, okay, reinforcement learning is like super high horizon problem, you need to plan over like millions of states and actions, and figures out a new architecture that has super good long range dependency capabilities, maybe that particular advancement could be useful for video generation or video captioning too, because videos are super high dimensionality as well. So this is actually our motivation for doing this work. If we actually put transformers in reinforcement learning, then, and if everyone starts to work on it, whatever advancements they make in NLP or vision or RL will be super easily like usable across each other. And that'll lead to faster progress too. And I actually have a bolder claim. This is probably the only way to scale reinforcement learning in the future, because fundamentally scaling is not related to like just your new algorithmic ideas. Very few algorithmic ideas actually pan out at scale. And if you wanted to come up with an idea that actually benefited from scale, there are factors beyond your control, which is like what is the hardware that and what is the software that scales the best, what is the how people actually scale the models, how people actually scale the data. And right now the largest scale activity in deep learning is happening in NLP, like large language models or like large image models and so on. So if reinforcement learning were ever to scale to that extent, like if we ever were to train 100 billion parameter models for agents, then it will likely have to be a transformer, because that's the only thing we know how to scale at that extent. So that's something that I kind of believe in. We'll have to wait and see. But a work like this might actually help people start building all the essential building blocks for that. And just as a recap, like reinforcement learning is the problem where you're given a state and you're sensing the state in the environment, you're taking an action, the environment returns to you a reward, and you're trying to optimize the reward. So a very simple summary of this is you try a few things in the world, you look at what rewards you get. If something is very rewarding, you do more of it. If something is not very rewarding, you try other things, and you usually keep adding noise to your actions. That's just called the exploration, and try to like build a good model of the world in order to achieve your plans. So this was a very interesting paper to many people, because it brought about this whole paradigm shift in reinforcement learning. Typically, reinforcement learning is like a whole bunch of algorithms. A lot of people have to go and read this Sutton and Bardo book, or like courses online, Berkeley, like DeepMind, blah, blah, blah. So there's so much of math in the policy gradient or actor-critic methods, Q-learning. And most people give up and they're not interested in it anymore, because it's much easier or lower barrier to entry to do something in NLP or GPTs or like image generation. Code bases are much simpler. So what if we can do the same thing for RL? Like you just say RL is just a transformer now. You look at all the past sequence of states, actions, and rewards, and you just output what you need to do in the future, output your plans. And just train a single transformer just like how you would train a language model. If that works, then you don't need all this Sutton and Bardo book. We're not there yet. Like the results are very encouraging now. Needs a lot more people to work on it and push the results. But if this does happen, and if this does scale, then that's basically a big paradigm change in reinforcement learning. And so the architecture is simply what I've been describing so far, what the GPT-3 API predicted it is. You take in the past sequence of rewards, states, and actions. You have a causal language model like transformer, and you're trying to predict just the future actions. You could also predict the future states if you wanted. That's a good auxiliary loss to have. We didn't feel the need for it. But what matters is you predict the future actions given the past sequence of states, actions, and rewards. And so given a data set of trajectories that the agent has encountered in the world, you can actually just break it down into these sequence of tokens and provide the target reward to go in the beginning, like say, oh, you go get a score of 100 or something like that. And the level of fine grain or very coarse level of detail in terms of what is the reward to get depends on the task or the task the agent has to do and the level of control you want over it. And if you have a sufficiently large data set and a sufficiently large model, this is literally like playing into the strengths of the transformer. The transformer can be thought of as a sponge for absorbing any kind of data. So this is exactly what it is doing here. And So yeah, the basic idea is replace RL algorithms with a simple transformer. The transformer will now learn what it means to do credit assignment. You don't have to like actually write down equations for, oh, the way to do credit assignment is to do bootstrapping with a value function, and you need to do variance reduction, blah, blah, blah. You don't need all that. The transformer will do that. All those, the algorithms will be written in the weights of the transformer, just like how Andre Karpathy says software 2.0. Like the weights are going to be the algorithm. And yeah, so credit assignment is learned for free, no value functions, no dynamic programming. And one flexibility of this model is at test time, you can ask the transformer to be bad too. It's not just, on the other hand, if you train a value function based policy, all it can do is be optimal. But this model can actually even be suboptimal if you provide the reward to go as be bad or like get a really low score. So we tested this in offline reinforcement learning, where usually you don't have to worry about the exploration problem. And in general, reinforcement learning in industry is moving towards this setting because people have realized that you can collect a lot of data for free or by paying some contractors and bootstrap a lot out of existing data rather than just learn everything from scratch. And so people have called this setting as offline RL, where you're already given a data set of agent trajectories. So using this, it's very convenient to train a decision transformer. One example is like, let's say you're just given random walks in a graph and you have all the data of like what is the final distance to the goal and what is this trajectory the agent took. You can use that and learn a decision transformer on that. And at test time, you just ask it to minimize the distance, and the decision transformer can do that even though it's only trained on random walks. So it's really understood what it means to travel to minimize a certain distance. Similarly, like we tested it on all the offline RL benchmarks, like Atari and Mojoko, and it actually is almost as good or much better than TD learning, which has been like tuned for several years or like months by so many researchers and like so much theory about it. We just actually just forked Andre or Hugging Face and just wrote the data loaders and it worked. And another thing that I want to emphasize is this is more scalable, right? So all the people don't really know how to scale those TD algorithms at scale, like run it on like billions of trajectories or something. We don't even have the infrastructure for that, whereas the infrastructure for scaling decision transformer is already there. You just have to like use NVIDIA's Megatron or like all the latest large language models infrastructure. And the flexibility part of it, what I mentioned is at test time you can ask it to get any reward, not just a good one or a bad one, and that is what is seen here. The green is the oracle, so that will just get whatever target return that you ask it, and the blue is the decision transformer, and the orange is like the maximum reward trajectory that was present in the data set. So you can see that on games like Sequest, even though the maximum is somewhere on the left, the decision transformer can extrapolate to target rewards that are not even in the data set that are much larger than the best trajectories in the data set because it's implicitly understood what it means to get that score. And in general, it's pretty staying close to the oracle. So it means it can even get a lower reward if you wanted to, get a higher reward if you wanted it to, and it can get rewards that are not even in the data set. And this property is only going to get better as it trains on more data. Think about this as like GPT -1 of RL or something, right? Like very little data. GPT-0, also GPT-1 was just trained on like 4 gigabyte of text, and now people are training on terabytes of text. So this is just like a very, very small step towards the scalability. So the corollary, another corollary from the success of the decision transformer architecture is supervised learning is all you need for offline RL. Like you just have to give the sequence model a class label of what is the reward it has to get or what is the task it's doing, and just train it like a conditional behavior cloning or a conditional supervised learning problem. And this was something I actually pointed out on Twitter too, and Oriol Vinyals, like the AlphaStar lead scientist from DeepMind, confirmed it. Like this was a trick that was actually used in training the DeepMind AlphaStar agents, where the AlphaStar the AI would get what is the number of units it has to build, and like what is the skill level of itself, what is the skill level of the enemy, and so on. And at a test time, you could ask it to like play it against a higher skill level than what it's trained on in order to be better. So these ideas are like already like being used in the most capable AI systems. And another example is the GitHub Copilot or OpenAI Codex. That it can be thought of as doing something like the decision transformer, where given some task or instruction in text, it's able to like write the code for it, and you can ask it to make it smaller. It'll do that by adding new code or crop it circularly. You can think of this as just like providing the reward or a task in text in the beginning, and it has the context of what's happened so far, and it's able to take future actions. So you can learn more about DTs. There's archive code. There's a Twitter thread from Igor explaining the paper. And also there's a video from Yannick Klucher explaining the paper. And that's it. I take questions, maybe one question maybe.